Hey, everybody. We're going a different direction today. We're going to talk about fluids. And to prepare ourselves to work with our neighbor, we're going to be doing a lot of little exercises with our neighbor. I'd like you to turn to your neighbors and find out what their middle name is. Find their middle name, everyone.
In my Instagram.
I think Evan.
Oh, you're right.
Okay. Were any of you sitting next to someone who did not have a middle name? Okay. We didn't give our daughter a middle name. We gave her the first name of Heidelinda. We figured a middle name after that would be cruel. So if you're sitting next to someone without a middle name, for today's lecture, just call them Nimrod. Okay, it means mighty hunter. It's an honorable thing. Okay. Okay. So, Sydney, you had a question? Nimrod. It's Evan. It's Evan. Okay. Is there a Nimrod in the room that's willing to give us an opening prayer? Okay, I'm a Nimrod. I'll do it. Our dear kind Heavenly Father, our hearts are filled with gratitude for the many blessings which have been bestowed upon us as members of thy church and as members of families, and we are grateful for the opportunity to be here at this university and to learn new things and to have important experiences. Father, I pray on behalf of these young people as they face the many challenges and decisions that are before them, that they might be guided and also comforted and lifted up, that they might be equal to the task. We ask that our minds might be sharp this day as we seek to learn new things. And this we pray in the name of Jesus Christ. Amen. Okay. I have kind of a different goal today. Normally, what I'm all about is trying to help you see that you can do it. You can understand this. You can get this figured out. But buoyancy that we're going to be talking about today, sinking and floating, you've covered that in 4th grade and the 6th grade and junior high. And so today, I'm going to actually be trying to convince you that maybe you don't fully understand buoyancy. And that's because on this next exam, not the one this weekend, but the one after that, the question that students have most difficulty with is the buoyancy problem. And when I asked my TAs, what part of the class was hardest for you?
Buoyancy.
Yeah, they all said that, buoyancy. And so I want you to approach this with a sense of humility that maybe I didn't learn everything about sinking and floating in middle school, okay? Maybe there's some nuance here, and we'll find that. Now, just to talk about quickly the exam, remember, it's entirely multiple choice. You're not going to be allowed to write on the exam. You need to bring scratch paper. You need to bring scratch paper, and they make you recycle the scratch paper when you're done. So you're going to walk out of there with nothing, okay? And and then they'll tell you electronically what your score was. After the test closes the following next Tuesday, they will also tell you which questions you missed, if you missed any. Let's just hope you didn't miss any, then it doesn't matter. But they also tell you what the right answers are. I will also have a video queued up and ready to go right when the test closes, so that you can go in and see why you missed any questions you might have missed. Again, not all the equations will be given, just the ones that are on the sample exams, and it will not cover the material we are talking about today. Are there questions about that exam before we launch into the new? Yes.
Closes Tuesday?
It closes Tuesday. I believe the testing center, the last time they'll hand out an exam is 9 o'clock in the evening. But remember, they close early on Saturday and they close early on Monday, so don't get yourself in a bind. Yes, they're on the sample exam, so they will be there on yours as well. Okay. Let's launch right into this. Talk to Nimrod about how you would find the area of something. If I had some shape, how would you find the area of it? Talk to Nimrod. Okay. Let's practice this. On the side, I sell farms, and I have 2 farms for sale. And both of these farms have exactly the same soil and water and other farm stuff that I don't understand because I'm a city boy. So they're identical in every way except for area. And so you want to figure out which one has the most area. Well, how many of you are sitting next to a Nimrod who came up with this formula? Length times width. Raise your hand. Yeah, okay. For you, I have a great deal. Look at farm number 1. Okay, if area is length times width, farm number 1 is whoa, better deal. Okay, so what you see is that length times width works great for rectangles, not so much for this shape here. For this shape here, what we're going to have to do is break it up into grids, where each of these little squares represents, say, an acre. Here, with farm number 2, I would just count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. When you find yourself adding the same number over and over again, that's the time to multiply. So I've got 8 across, 8 up, 8 times 8 is 64. That was easy. But for farm 1, I can't pull that trick. I got to count them. I've got to, okay, so there's 2/3, there's 1, there's 3/4. I've got to carefully count them and add them up. So that's why for rectangles, we can get away with just the multiplication length times width, but not for other shapes. Now, we're not here to talk really about area, but rather about volume. And we can generalize what we just talked about. These little cubes, these little plastic cubes, are 1 centimeter by 1 centimeter by 1 centimeter. We call them cubic centimeters, if you'll believe it. And if I wanted to find the volume of this odd-shaped little pumpkin, what I could do is make a big cube out of these 1 centimeter by 1 centimeter by 1 centimeter cubes. I could make a great big block of them, and then I could take out a knife. Whoa, back, he's got a knife. And I could carve an exact duplicate of that guy out of these little plastic cubes. And then after I had made my duplicate, I would pull apart all the cubes and count how many I had, being careful to say, well, this one's only a half cube, this is 2/3 of a cube, and so forth. And so you get the idea of how you would find the volume of that. Now, this is the first way to find the volume. The volume of an object is just the number of unit cubes, 1 centimeter cube, that it would take to duplicate that object. Now, I'm going to do something that I call the 75-25 rule. And the reason I call it this is that when I do this demonstration, 75% of you are going to be saying, I've known that forever, Greg. That's just obvious. That is so simple. And 25% of you are going to have a mind-blowing experience. Whoa. Now, here's the thing. When I do this demo, you don't want your neighbors to know that you're having a mind-blowing experience because you should have had it years ago, okay? So everyone just stone face, don't look at Nimrod, just look forward and pretend you have known this forever. I have 2 containers of the same size and shape, but one of them has 1 kilogram of lead shot in it, and one has 1 pound. And you can see that a kilogram weighs more than. Batman, can you see that back there? Yes. Okay. They are indeed different weights, are they not? Okay. The pirate says yes. We can also demonstrate that they are different weights with that. Now, here's my question. Both of these beakers are filled halfway, 500 milliliters of water. When I put these in the beakers, in which beaker is the water level going to go up? Do not talk to Nimrod. Do not look at Nimrod. Just watch. Everyone have their prediction in their head? Silent? They went up the same. Of course they did, Greg. Of course, I've known that forever. And that's because where that bottle is now, water used to be, and it had to go elsewhere. And because the bottles had the same volume, they displaced the same amount of water. It had nothing to do with how heavy they were, as long as they both sank to the bottom. Okay, don't talk to Nimrod. Do not talk to Nimrod. Okay. Now, this gives us another way of finding the volume of something. If we submerge it in liquid and just look at how much water or liquid was displaced, that's going to give me the volume. So what I could do is fill something up to the brim, put my object in, and see how much liquid spills out. And that's the volume of my object. Now, I didn't always understand this. I was taught this by a very, very wise and loving, wonderful woman, my grandmother. When I got back from my mission and before I got married, I lived in her basement, and she was the best baker in the world, best baker. And I asked her if she would teach me how to bake an apple pie. And you know that the key to baking an apple pie is getting a nice, fluffy crust. Okay, and the key to doing that is getting just the right amount of Crisco, which is a polite way of saying lard. Okay, and so my grandma told me to get a cup of Crisco. So I took a cup and I started scooping Crisco out of the can and pushing it in. And any of you that have done this know that you get air bubbles in there, and then you're trying to get those air bubbles out. And my grandmother actually laughed at me. I mean, it wasn't with me at all. It was at me. And she had never done that before, and that hurt. Okay. But she said, Greg, that's not how you do it. And she took this great big measuring bowl, she filled it up halfway with water, and then she just started shucking the Crisco in there until it went up a cup. I said, Eureka, that's wonderful. Okay, and just to prove that I can do this, I made that pie. Yeah. Okay. Now, some of you are seeing a pie in the pie and you are geeks, okay? Celebrate your geekness. Okay. There we go. Now, my grandmother, wise as she was not the first person to come up with this, obviously. That would be Archimedes. And I think most of us have heard this story before, but we're going to hear it again. It turns out that Hero of Syracuse wanted to place a golden crown in the temple to the gods. So he measured out a certain amount of gold, gave it to an artist, and asked him to make him a crown. The artist came back with this beautiful, beautiful crown, and the mass of the crown was exactly the same as the mass of the gold that Hero had given him. But Hero was suspicious that maybe this artist had robbed him and replaced some of the gold with silver. Why? Because he was an artist, okay? So he called in the local smart guy, Archimedes, and asked him to determine whether the king had been cheated or not. As the story goes, Archimedes was thinking about this when he went to the bathhouse. And as he lowered his body into the bathtub, water spilled out. He suddenly had this great aha, and the story goes he jumped from the bathtub and ran naked through the streets of Greece, yelling, "Eureka, Eureka." That wasn't a big thing back then. They didn't worry about that. So he goes back to the king, and he proposes the following test. He takes a lump of gold and a lump of silver, each which have the same mass as the crown, and he takes a big old bucket and fills it with water, and then he measures the water which runs out when he puts in the silver lump, and then he does it again for the gold lump, and then finally he does it for the crown. And what did he find out? Who knows the end of this story? Had the king been cheated? Yes, he cheated the king and he lost his head. Okay, that's end of story. Okay, so be careful what you when you cheat a king. Okay, let's talk about this idea of density. What Archimedes was finding was that the crown had a density that was different than the density of gold. And he knew that gold and silver had a different density. But what is density? Well, if we went back to that pumpkin that I had made out of these cubes, if we wanted to know the density, what we would do is carve out one of these, we'd carve out a chunk of the pumpkin that was 1 centimeter by 1 centimeter by 1 centimeter. And then we would put that on a scale and find out what its mass is. And that's all density is. It's the amount of mass in 1 unit of volume. Now, folks, the actual scientific unit for volume is the meter cube. But we find, and all scientists find, that when you're talking about fluids, it's just more useful to talk about centimeters cubed instead of meters cubed. And we're going to find that we're going to have to take that into account when we use our equations. Now, the reason for that is that the density of water has a very easy value to use. Anyone know what the density of water is? 1 point what? 0. 1.0 what? 1.00000 to infinity and beyond. Okay? And I can write that as 1 gram per cubic centimeter, or 1 gram per centimeter cube, or for those of you that are planning to be doctors, 1 gram per milliliter, a milliliter centimeter cube, potato. Okay? Now, it's not just any water, it's special water. Anyone know what has to be so special about this water? Raise your hand, brave Nimrod. Yes, sir. It has to be distilled water. It's better if it's distilled water, but that's not the biggest factor. What else? What else is about it? No one? What's that?
It has to be a certain temperature.
It has to be a certain temperature. That's the biggest thing. It has to be exactly a certain temperature. And that temperature is anybody? Yeah. It's kind of different. Your intuition wants you to say, well, zero degrees centigrade, where water freezes. But it turns out that water is very, very different than other liquids. Most liquids get more and more dense as they get colder and colder. Well, water does that until it gets to 4 degrees. And then it starts expanding and getting less dense down to 0. And that's what keeps us alive on this planet, okay? If water behaved like other liquids, then the ponds and the lakes would freeze from the bottom up. Okay, the water that was coldest would be densest and it would sink to the bottom, and then you would just freeze from the bottom up and essentially wipe out all your fish. Because water has this property of getting more dense down to 4 and then getting less dense, the water, when it gets to 4 degrees, sinks. And that allows the water at 0 degrees to freeze over the top and give you an insulation that protects the rest of the fish. If your neighbor Nimrod followed that argument. Okay.
It's a basic question.
Ordinance is 4 degrees. Tell you that there's a guy, I don't know what works.
Now,
Feeling like you're.
if you want to use this principle to cheat at Trivial Pursuit, next time you're playing with friends, just pick up a card and pretend to read it, but instead ask, what was the temperature at the bottom of Lake Tahoe on August 7th, make up a year, 1935? Okay. And the answer is 4 degrees. Lake Tahoe is so deep, the water there at the bottom never warms up past the greatest density of 4 degrees. So you'll win every time unless you're playing someone else in the class, and then they'll know it. Now, it turns out that in the standard units, this is 1,000 kilograms per meter cubed. Now, if you think about a meter cubed, a meter's about this big. Meter cubed would be this by this by this. 1,000 kilograms. That's a lot of mass. And that's why your landlord doesn't want you to have a water bed on the 2nd floor. Okay, that's just kind of rough on the structure. Okay, we're going to be using the 1 gram per cc because that's so easy to use. Let's do a clicker question. We haven't done one yet today.
It's already.
Okay, now you can click. Which has the larger density, a cup full of water, a lake full of water? The cup, the lake, or they both have the same density?
Yeah, no, I know.
Okay. Again, this isn't rocket science. We did that last week. Last call. Get your vote in. Good, good. The answer is C. And if we had all gotten that correct, we would have all gone to Disney World, but there were 22 of us that kept us from going to Disney World. I'm sorry. Okay. The point of this slide is that density is a property of a substance, not an object. Everything that's made out of brass is going to have the same density. Everything made out of the same kind of steel is going to have the same density. Now here we are assuming that the cup full of water and the lake full of water have the same temperature. And those of you that have, taken a dive into a lake know that that just ain't always so. But we're going to ignore the temperature differences in this class, in the homework, and on the exams. We've got enough to worry about without that. Okay. When we talk about fluids, we're talking about both liquids and gases. And anything that conforms to the shape of their container, we call a fluid. Now, a liquid is different from a gas in that a liquid will take the shape of the container, but not change its volume. Its volume will stay the same. And that proves that cats are liquid, if you'll believe it. Now, any of you scuba divers? Okay, you know that that when you go diving, there's pressure, okay? And that pressure can actually be painful if you've got clogged sinuses or something like that. And my question to you is, what should matter? What determines how big that pressure is as you are in the water? Talk to Nimrod. What factors are important?
What factors are important?
There's 1,000 factors. Yeah, but I guess.
Makes sense.
Your skill is ridiculous. You can go to.
I'm gonna be dropping everybody diagram.
Okay. Brave soul, raise your hand. Share with us. Brave soul, where are you? Don't be afraid. What? Yes, sir.
Sure.
What's that?
Sure.
Temperature? Okay. What else? Nothing else? Just temp, yes.
Weight of the water on you.
Okay. And that's going to be greater the deeper we go. Okay. What else? I'm sorry, I don't hear well. Raise your hand. What was this? Sam, what else? Depth. She already said that. Okay.
Gravitational acceleration.
Gravitational acceleration. That's a good one. Yeah. What planet you happen to be on? Okay. That can change if you are rich enough. Musk has taught us that. Okay. Let's talk about it. The pressure in a fluid. It's just the magnitude force of that fluid acting perpendicular to a surface divided by the area of that surface. Okay. And it depends on the depth of the point beneath the surface and the density of the fluid. And we'll find out also the planet that you're living on. The depth is easy to demonstrate. If I have water in this container and I open up 3 different openings, what we find is that the deeper we go, the greater the pressure. And you know, that demo is just going to disturb us if we keep it going. We're all going to be uncomfortable. Okay. There we go. Okay. Now, my friend Jeff Adams, when he was a teenager, decided that he was going to explore the lake that his family's cabin was on. And he was going to do it in a way that was ingenious. He was surprised that Jacques Cousteau had not thought of this before. He went and got himself a garden hose and a big old piece of styrofoam. And he put the garden hose through the styrofoam, put the other end of the garden hose in his mouth, weighted down his feet, and walked into the lake. How did that work out for him? Did it work? No. If you think about the two ends of that garden hose, down there where Jeff is, there's a high pressure on the garden hose, and up at the top there's a low pressure. So which direction is air going to travel through that garden hose? Up. This is a great way of getting all the air out of the Jeff, okay? And that's the way it worked, and that's why Jacques Cousteau doesn't do it this way. So that's just a bad idea. You don't have to make all your own mistakes. You can learn from us old people. Okay, let's determine how this pressure changes with depth. And we're going to do it in such a way that it's really quick, very easy to understand. No one's going to be hurt by this derivation. What we're going to do is we're going to go down to a pond, and with our mind, with our imagination, we are going to carve out a block of water, and that block of water is going to have dimensions A on the bottom, A on the top, and H on the sides, okay? And we're going to isolate that block of water, again, in our mind, and draw a free body diagram for it. Now, it turns out we have two forces down. We have the weight of that block of water down. We also have the water above the block that is pushing down on this surface. We only have one force up, and that's the water down below the block pushing on this surface up. Now, we also have a bunch of forces on the sides, and you're going to talk about those in this week's tutorial, and they're going to all cancel each other out. So we just need to talk about the vertical forces. Now, if we draw a free body diagram, there's our two forces down, and there's the one force up. Now, the thing about this block of water is it don't know it's special. It don't know that it's different from the other neighbor water. And so it doesn't accelerate up, it doesn't accelerate down, it just sits there. And so that means that this diagram has to scream balance. That means the one force up has to balance the two forces down. Now, see if Nimrod can see why pressure times area is a force. Talk to Nimrod. Why would that be a force? Pressure times area.
Based on the pressure. On it everywhere.
Pressure times area force. I think it's just because the pressure each part or area.
Okay.
Area is this big. It's gonna pressure's gonna be pushing just that much, but if it's that big,
Since pressure is how much force I have per unit of area, if I multiply by how many units of area, that'll give me the total force. Now let's do something with this equation. The mass I can write as the volume times the density. Remember, the density is how much mass I have in 1 unit of volume, and then I multiply by how many units I have, how many of these little cubic centimeters I have. Now I'm going to replace that, and then the volume is just going to be the area of the top times the height of that block of water, and I replace that. And now you see the magic. The area cancels out, because it doesn't matter whether you go down 10 feet in a pond or 10 feet in the Great Lakes. The area of the lake or the pond totally irrelevant. And so we get this formula. That's one of your key formulas in this part of the class. The pressure at a point 2 is equal to the pressure at point 1 plus this factor of rho times G times H. So it depends on the density of the liquid, it depends on what planet you're on, and it depends on how deep you go. Now again, it also depends on temperature because this rho depends on temperature, but we're going to ignore that in this class. We're not going there. We're always going to assume the same temperature for our liquid. How we doing? We on the bus? Okay. Yes, sir. What's that? That symbol there? That's rho. Oh, I'm sorry. Rho is the density. That's the symbol we use for density. It's the Greek letter R. And that just means the amount of mass per unit of volume. Now, how do we use this? Well, if we know the pressure at any point in a liquid, we can plug that in here. And then we can find the pressure deeper in the liquid by just using this formula. Now, typically, what we do is we put point 1 at the top of the lake. Is the pressure there 0? No. When you're at the top of the lake, you're at the bottom of an ocean of 30 kilometers of air. And that ocean of air is constantly pushing down on us. And it's pushing down with what we call the atmospheric pressure. Now that atmospheric pressure, this is a number that will be given to you in a problem if you need it, but it is 101,325 newtons for each meter squared. Now, typically, since, well, we call this combination newtons per meter squared a Pascal to honor a dead physicist. Some consider him a chemist, but we're going to say he's a physicist. We claim him. Now, because the Pascal is a small unit, we typically talk about kilopascals. And so often we will just write 101 kilopascal. And this is the number used in all of the industrialized nations of the world, except one, America. What's atmospheric pressure in America? 1 atmosphere is what? What would the units be? Not newtons per meter squared, but pounds per square inch. And how many pounds per square inch are pushing on us? Nobody? Oh, this is a new number for you. 14.7 pounds per square inch at sea level. It's going to be a little bit smaller, I think 13.9 here up in the mountains. Now, we can demonstrate this pressure by crushing a can. Right now, I have an empty paint can, and it has air on the inside, it has air on the outside. The air on the inside is pushing on every square inch with 14.7 pounds. The air on the outside is pushing on every square inch with 14.7 pounds. And so it's just hunky-dory. But if I take the water, I'm sorry, take the air out of the inside, and there we go. Okay. Now, we can also do that at a larger scale. I have on occasion brought in a 55-gallon steel drum and collapsed it. But because I did not have a 55-gallon drum today, I've got a video of that. And so What I'm gonna do in this video is I'm going to put a couple of inches of water into that drum, put it on a heat source, and get that water boiling so that I've got steam coming up out of the top of the drum. That steam is, well, it's water vapor. And as it rises, it pushes the air out of that drum. And then after I've been boiling that for about 20 minutes and I've gotten all the air out of the drum, I cap off the drum and take it off of the heat. And then I cool down the water vapor inside with ice or liquid nitrogen. And then it turns back into water, leaving a vacuum behind. So let's watch that. Oh, looks like I don't have a click thing there. Now, some of you are saying, well, let's do it bigger. Let's do it bigger, okay? That's what the can looks like afterwards. So how did they do that? Well, they steam cleaned the inside of that tanker car, and instead of letting it cool and vent, they capped it off so that it was just filled with steam that then cooled down and created a vacuum. Now, this wasn't an accident. You saw all of those Germans out there with their umbrellas. They were waiting for this to happen. Why would you take a perfectly good tanker car like this and implode it? Well,
It's
for a movie. Okay, for a movie. Want to see that again? Yeah.
transport.
Yeah. Physics is useful. Okay. Now, the first person to demonstrate this atmospheric pressure was Otto von Guericke. It's an umlaut. We call this the Magdeburg spheres because he did it in the city of Magdeburg. He took two hemispheres, and they are not locked together by any bolt or anything. There's just a little layer of grease to get them a good seal so that air could not get in or out. And then what he did is he pumped all the air out of that sphere, and he hooked up each half of the sphere to a team of horses, and the horses could not pull it apart. And that's how he demonstrated this 14.7 pounds per square inch. Now, in the 70s, when I was alive and a teenager, this became one of the most famous ad campaigns in all of history. They replaced the Magdeburg sphere right there with a pair of 505 Levi jeans. And this picture right there just went throughout the world to show that Levi jeans were really, really strong. Okay, that's not going to be on the exam. Okay, how deep do you have to go in a liquid before you change the pressure from 1 atmosphere to 2 atmospheres? Those of you that are scuba divers should know the answer to this. Raise your hand if you know what the answer is. How deep do you have to go to? Yes, sir.
10 meters.
What's that?
Meters.
10 meters. Good job. Good job. Okay. 10 meters. Now, this is the way we calculate that. We use that formula for pressure, and we plug in 1 atmosphere here and 2 atmospheres there. Okay. And then we subtract an atmosphere from both sides of the equal sign, and we get this. And then we solve that for H. And we just have 1 atmosphere divided by, this is the density of the liquid we're in, and that's the gravitational field strength, what planet we're on. Now, because we want a fairly accurate depth, we're going to use 9.8 here instead of 10. And because this is in newtons per kilogram, we have to use our density in units of kilograms per meter cubed. And that's 1,000 if we've got fresh water. And when we solve that, we get 10.3 meters. Well, this gentleman said 10 meters. Was he wrong? No. He was just smart enough to always go scuba diving in salt water, because scuba diving in a freshwater lake is boring. It's just mud, okay? If you do the same thing with salt water, it's 10 meters, okay? And that's what we remember as scuba divers, because that's typically what you're diving in. But what if perchance you stumbled upon a pond of liquid mercury and you said, hey, I'd like to go diving in that? How deep would you have to go to increase the pressure from 1 atmosphere to 2 atmospheres? Not very far, not very far. It's a number that you've probably heard before. It's 76 centimeters or 0.76 meters, okay? And actually, 76 centimeters of mercury is kind of famous, because back in the day, we used to use mercury to measure atmospheric pressure to tell us when a storm was coming. What we would do is take a very long tube, longer than a meter, and fill that with liquid mercury. We would then put a bowl on top and turn it all upside down. The mercury would fall, leaving a vacuum up here, so pressure 0. Right here, the pressure is 1 atmosphere if you're at sea level, and that means that this column is going to stop falling when the pressure right there is 1 atmosphere. Well, if the pressure there is 0, it's going to take 76 centimeters of liquid mercury to take it from 0 pressure to 1 atmosphere. We could also call that 760 millimeters. or 1 torr. Now, we don't do this anymore. Does anyone know why? Tell Nimrod why we don't do this with liquid mercury anymore. Okay. It turns out that this above the mercury is not really a total vacuum. There's a very small vapor pressure of that mercury, and it's toxic. It causes brain damage, okay? Now, we didn't always fully appreciate that. And back in the day, when I was again a teenager, my father, being a dentist, would often bring liquid mercury home because they used that when they made fillings. They would mix that with the silver to make those fillings in the olden days. And my brothers and I would play with this mercury on the kitchen table while we were waiting for dinner. And that explains me and my brothers. Okay. Okay. Now, funny quick story. I was teaching at University of Washington 34 years ago, and we were talking about temperature with these high school teachers that were taking a class, and we had a bunch of thermometers that were old school that were filled with liquid mercury. And an accident happened where this whole big container full of these thermometers fell on the floor and just shattered, and there was mercury all over the place and glass. And so I'm there on the floor trying to push all this mercury together to collect it. And the next thing I know, there's sirens and everyone's evacuated out of the building. And these people come in with these spacesuits on to clean it up. But I'm there playing with it just like I was with my brothers. Okay. Now, we're going to talk now about sinking and floating. And I'm going to introduce this topic with a little story. I went to high school, as I told you, on the island of Guam, and just down the cliff from our house was the most immaculate, beautiful beach on the island. And often when you come into my office and I'm smiling, I'm there. That's my happy place. So let's imagine I'm down there on that beach, and for whatever reason, I pick up a great big boulder. And I walk towards the ocean. Oh, and the sand is hot. The sand is hot. But now my feet are in the water and it feels good. It feels cool. And then as I go deeper in the water, a magical thing happens. I become stronger. The boulder is no longer as heavy as it was. What is so magic about that water? Why is it not heavy anymore? Buoyancy. Buoyancy. Okay. And that's what we need to understand today. There's the water and there's the boulder. That's what boulders look like in Guam. Okay. And what I've represented here is the push by the neighbor water. Now, you see that the deeper we go, the bigger the water pushes. And that's why the push from the bottom is greater than the push on the top. Now, if I take all of those pushes and add them together, I can lump them into one upward force, because these are bigger than that we call the buoyant force. The buoyant force. Now, the first person to tell us how big that buoyant force is was Archimedes. And he did it in a very similar way to what I'm going to do, but with different language. I'm going to have us consider something that I call a Casper box. This box is 1 meter by 1 meter by 1 meter. It's a cubic meter, if you will. And by Casper, I mean Casper the friendly ghost. That's fitting for today. And you remember, if you do, Casper, you know, he was a ghost. He didn't have any mass, but he could hold things. You remember every now and again, they were chasing around the cat and the mouse and everything, and they would knock the goldfish bowl, and it would go into Casper, and he would have the water inside him, and the fish was going. Have you seen this episode? Okay, so the Casper box has no mass, but just holds stuff. If I fill that Casper box with water, and I ask myself, how much does that water weigh? Well, tell your neighbor, tell Nimrod. Remember, the density of water is 1,000 kilograms for each meter cubed. So I have a mass of 1,000 kilograms of water. How much is that going to weigh? Shout it out. 10,000 newtons. So that's 10,000 newtons. Now here's the genius of Galileo, not Galileo, Archimedes, different smart guy. He said, that water's not going anywhere. It doesn't know it's special. It's not going to go up. It's not going to go down. So the buoyant force has to be 10,000 newtons on that Casper box. And then he said, well, what if instead of water, we put steel in the Casper box? Well, steel has a density that's 7.8 times that of water. So the weight of that block of steel is now going to be not 10,000, but 78,000 newtons. But the buoyant force doesn't care what's in the box. It's just the neighbor water pushing, and it pushes the same whether it's water in the box or steel in the box. So the buoyant force is still going to be 10,000 newtons. And that box of steel is going to accelerate down to the bottom of the lake. Okay? Now, on the other hand, if we fill that Casper box with styrofoam, styrofoam having a much smaller density than water, now the weight's going to be smaller than 10,000 newtons. Let's say 1,000 newtons. I just made that up. But the buoyant force, again, doesn't care what's in the box. It stays the weight of what we had when we had water in the box. And so that's going to be 10,000 newtons again. And this box of styrofoam is going to accelerate upward and float. I like this Far Side cartoon. Embedded in styrofoam shoes, Carl is sent to sleep with the human. Okay? He's on his way. Now, this is Archimedes' principle in a nutshell. The buoyant force acting on an object is equal to the weight of the fluid, either the weight of the fluid displaced by the object or the weight that would fill the Casper box that's the same shape and size as the object. Okay? As a consequence of this, anything that has a density greater than water will sink in water. And anything with a density smaller than that of water will float in water. And that's what you learned, I think, in junior high. That's the level where we were at. Now, we can practice this principle with this column of liquids. If I have salt water with a density of 1.2 grams per centimeter cube, I can float on top of it, if I'm careful, some fresh water with a lower density, and on top of that, some oil of an even lower density. I have 5 objects, A, B, C, D, and E, and their densities are given. Tell Nimrod where each of those is going to end up if I drop it into this column. Talk to Nimrod.
Yeah, you did start it. So we take it out of the shaker, put it in OD and again. Went to a jazz school tonight. It's a trash. Upper bowl, but.
Okay, let's talk about it. Object A has a density less than that of oil, so it will float on oil. Object B has a density greater than oil, so it will sink in oil. but its density is less than fresh water, so it will float on fresh water, sink in oil. C has a density greater than fresh water, but less than salt water, so it ends up there. Both D and E have density greater than all of the liquids, so they end up at the bottom. Now, what you'll see is that nothing ends up in the middle. Everything always floats on top or sinks to the bottom. In order to get a block to stay right here in the middle, it would have to have exactly the same density as water. And that's what we do with our vest, our flotation vest, and our weight belt when we're scuba diving. We have to very carefully adjust our density so that we're neutrally buoyant, so that we're not constantly floating up to the top or sinking down to the bottom, so that we can enjoy the experience, okay? But it's very, very rare that something's going to have exactly the density of that liquid. And so usually everything ends up at the top or down at the bottom. Now, how many of you saw the movie Jaws that came out while I was a teenager on Guam? That scared me to death, okay? And the scariest part of that movie was when the sheriff goes down at night looking for the body with a flashlight. And he finds the body, but not all of the body, just the top half of the body, because she'd been bitten by the shark. And there's that music, no, 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 no. You're scared to death. And he turns with the flashlight, and there she is. And she's not on the bottom, she's not at the top, she's in the middle. Would Hollywood lie to us? Yeah, they would, but not in this case, because they were taking into account the fact that in a real lake with real water, there are what we call thermal layers. And you've experienced this if you've taken a dive into a pond or a lake. You've got this layer of warm water that's been heated by the sun, and then it seems like you go through an invisible kind of a barrier, and then it's really cold, okay? And those two levels or layers are going to have different density, like this. And so that body was floating on a higher density cold layer and sunk in a lower, yeah, you know what I mean. I can do that here. I've got some beads, blue and white. And up here, I have some, this is some methyl alcohol. And down here, I've got some salt water. And if I take that all up, it's all random. But it turns out that all the white goes up here, all the blue goes down there, and then watch what happens. They move together. And what happened when I shook it is I mixed the alcohol and the salt water together. And so now I've got a layer of alcohol, a mixture, and salt water. And then what happens is that the mixture separates and all of the alcohol goes up and all the salt water goes down. And you've got 4 layers: salt water, blue beads, white beads, and alcohol there. We can also show this with this demo where I've got this dark colored ball, and it's got these little glass beads. If I can change it into gold because I'm magic. Yeah. What we did is we just, the gold has a smaller density. It floated in the beads. The dark colored one had a greater density and it sank. Okay. Is that a sinker or a floater? Well, the density of steel, we said, was 7.8 times that of water. So it has a density greater than water. Maybe it should be a sinker. But Lloyd's of London would like to call it a floater. What we need is a different definition of sinking and floating. If a giant hand takes that boat down to the bottom and turns it around and around and around till all the air bubbles come out and lets go, if it stays down, it's a sinker. If it comes back up, it's a floater, okay? So with that definition, let's talk about this one here. These pictures came over the inner tubes a while back. This boat was coming down the river and someone forgot to raise the drawbridge and it bounced into the bridge. It goes under, and then it comes back up. That's a good boat. That's a floater. Okay. So the buoyant force is greatest on a 10-ton ship if it's floating in freshwater, saltwater, liquid mercury, or all the same. Now you can click.
Have you ever swam in this?
Okay, last call, people. Okay, get your vote in. I'm pushing the button. Okay, liquid mercury. That's not the right answer. The correct answer is all the same. Whoa, wait a minute. How can that be? Well, if we look at a free body diagram for the boat, we have a weight down, that's going to be 10 tons because it's a 10-ton ship. And then we have the buoyant force up. And if it's floating, what's the acceleration for a floating boat? 0. And so that means the buoyant force has to be 10 tons, whether it's floating in freshwater, saltwater, or liquid mercury. So what does change? Well, what changes is how high the boat is floating. If it's in a freshwater lake, it has to float low because it's got to displace 10 tons of water, and that's a whole lot of water. But if it's floating in liquid mercury, heaven forbid, well, it doesn't take very much liquid mercury to add up to 10 tons, so that boat would be riding high, and indeed, maybe it might not even be stable. It might tip over in the lake of liquid mercury, okay? Where are these people floating? Either Great Salt Lake or the Dead Sea. Those are the two places where you can do that because the concentration of salt is so high that the density of the water is great, and so they float high like that. So here I have a beaker of water. I have 3 blocks that are all the same size and shape, one of aluminum, one of steel, and one of wood. And the question is, which block has the greatest buoyant force? Tell Nimrod. Talk to Nimrod.
It's just like you can see it. The buoyant force comes from the.
Okay. If you said the wooden block, slap yourself hard, okay? Remember, the buoyant force is the weight of the fluid displaced. These 2 blocks are both displacing their entire volume of fluid. Okay, where they are now, liquid used to be. The block of wood is floating such that half of it's below the surface, half above. So only half of that wood is displacing liquid. So whatever force I have on the steel block, I'm going to make up a number, 8 newtons. I would have the same 8 newtons on this block, buoyant force, and I would have only half that much, or 4 newtons, on that. So why is the wooden block the one that floats? Because its weight is only 4 newtons, whereas the block of steel and the block of aluminum have very much higher weights. Now, you know the answer to this because I just gave it to you. Which of these blocks of wood experiences the greater buoyant force? Both of these blocks have the same volume, but they're not floating the same. Which block has the greater buoyant force? Everyone should get this right because I just gave you the answer. We're gonna go to Disney World, people. Make it happen. Make it happen.
These didn't. I was like, I still think.
Okay. Here we go. Closing it up. Last call. Oh, I'm sorry. We're not going. Oh. These people had my back. They knew I couldn't afford to take you all. Okay. Quick announcement. Yesterday, I got approval to open a third section of 106, opening up 240 seats. Everyone's going to get into 106 that wants to get in. Yeah. Yep, yep. That means you get to be doctors. Okay. Now, if we look at those two blocks, by Archimedes' principle, the buoyant force is the weight of the fluid displaced, and because this one is displacing more fluid, it's got the bigger buoyant force. Now, by Newton's second law with zero acceleration, that buoyant force has to be equal to the weight of the object if they float, okay? And so these two blocks can't be the same type of wood. The one on the left might be oak, a very dense wood, and the one on the right might be balsa, a very not dense wood. Now, what should I remember? Archimedes' principle always applies whether something sinks or floats. The buoyant force is always, always, every stinking time equal to the weight of the liquid displaced. If an object floats, if it floats, and only if it floats, you have one more tool in your toolbox. That buoyant force is also going to be equal to the weight of the object, because a 10-ton ship has to have a 10-ton buoyant force to float. We're going to skip that. Folks, in the last 2 minutes here, I'm going to give you a problem that you can think about over the weekend while you're preparing for that other exam. You're floating a boat in your very own swimming pool. You're rich. There are 6 gold bricks sitting in the floor of your boat. You're rich. You lean over with a marker and you mark the water level on the side of the pool. And then you throw the bricks of gold to the bottom of the pool. Does the water level in the pool go up above your mark, go down below your mark, or stay put? With your clicker one last time.
So sad. It's a tragedy. What I said, yeah.
Okay. People, if sinking and floating were just as simple as you thought it was in the 8th grade, every one of us would get this right. We didn't. Okay? 28 of us got this right. We'll talk about this on Tuesday, folks. Have a great weekend. Happy Halloween.